Okay, our next talk is by Sergej Flach, Thermalization, Universality Classes for Weakly Non-Integrable Many-Body Dynamics. Sergej?
Yeah. Okay. So the story I'm telling you here started maybe 6-7 years ago. And started with David Campbell and Carlo Daniele. And then we realized that we are after something maybe more interesting than we initially thought it was. And then many more people joined. Mithun, who is here in the audience, and in the meantime back to India, was a postdoc with us at that time. Many more people. You see some prominent people, Michael Fistul, Boris Altschuler, and Emil Yushbashian, Barbara Dietz, but also young people who did the main work which I will present here, Mirab Maleshava, Weihua Zhang, Gabriel Lando, and very recently also Aniket Patra joined us on this trip. So, what am I talking about? We want to understand how a large many-body interacting system will slow down its thermalization upon reaching an integrable limit. What do we mean by that? We want, or what do we are after? We want to see whether there are different classes of non-integrable perturbations which will show you different, so to say, types of thermalization which will slow down in different ways, in qualitatively different ways upon approaching some integrable limits. So for that, we have to actually somehow quantify and tell what we mean by thermalization and quantify this process. And then, of course, we will head for novel dynamical regimes. So what am I talking about? I'm talking about large systems, ideally infinitely large. On a computer, we can only deal with finite but as large as possible systems. We want to discuss only microcanonical dynamics of closed systems. We will consider any system which is typically non-integrable, and then we will try to tune a parameter which will bring it close to an integrable limit. I remind you, integrable systems, Hamiltonian systems, will have a proliferating number of conserved quantities. And if you go away from the integrable limit, the usual assumption is that all these integrals of motion will not anymore be conserved, except for a few ones, especially, of course, the energy. And therefore, the system will show some reasonable type of thermalization. And it's clear also that as you come back to the integrable limit, all these integrals of motion, which are integrals of motion at the limit but not off the limit, will fluctuate slower and slower, and therefore at some point when you reach the limit, these fluctuations will take endless, and therefore the thermalization must take more and more time and in some sense diverge. Right. So what do you mean then by measuring thermalization? Thermalization is actually a buzzword which helps you maybe to publish a paper these days, but it's not very clear what it means for especially a closed Hamiltonian system. So here's what we mean. We want to measure timescales. Our system evolves endlessly, and we want to measure timescales. Which timescales? We can, for instance, choose some observables which we like, and look how they fluctuate in the system, and then measure their time averages, and simply wait until these time averages somehow become more or less equal to their ensemble averages. And then we will scream, hooray, because the system is ergodic, and we establish thermalization. So that means we follow time averages and somehow have to figure out when is the time when these time averages become somehow equal to their ensemble averages. This will never happen on any finite time, as you know, because ergodic theory only tells you that infinite time averages will be equal to phase space averages. So you have to somehow extract timescales out of this process of getting closer and closer of the time averages to their ensemble averages. The other way is to simply measure Lyapunov spectra, not just one Lyapunov exponent, but the entire spectrum, invert the entire spectrum, and get a set of timescales, which we will call then Lyapunov times. So that's what I mean by measuring or quantifying thermalization. Now, as we come closer to an integrable limit, it is reasonable to assume that all these timescales will diverge. And then we may ask, how will they diverge? Is it a power law? Is it an exponential way in which they will diverge? Are there differences? Are there different classes of weak non-integrable perturbations which will lead to different types of divergences. This smells a bit like half of a phase transition. When you approach a phase transition from one side, you will also see some kind of critical slowing down. The only difference is we can't go on the other side. But in a sense, we ask the same question here, whether there are different universality classes which may show different slowing down behavior. And you may guess that the answer is, to some extent, yes, which was quite unexpected for us. Right, and before I lose you, here's a nutshell summary what we actually found. So we found so far two different classes of weak non-integrable perturbations, which give us qualitatively different slowing down of thermalization processes. One of them comes under the nickname of long-range networks, and I'll explain you what I mean by that. And in this case, you have one diverging timescale which controls all other timescales of thermalization upon approaching an integrable limit. And the second class is a short range, comes with the nickname of a short-range network. Again, I will tell you later what that means. And that means that there is more than one time scale. There is actually probably another length scale, or I will show you later, an exponential decay of other time scales compared to a given leading time scale, which will all then control the thermalization dynamics and its slowing down upon approaching an integrable limit. Now, if you ask what does it mean from a physical point of view, where can I find these long-range and short-range networks, which are defined more in a mathematical way? Well, here are some examples. If you take an ordered system, an ordered large system, which is translationally invariant, and you add weak nonlinearities to that, then okay, generally you will get some system which is non-integrable and therefore will show nice thermalization. And if you now reduce the strength of this nonlinearity, you will find long-range network behavior. And weak nonlinearity on the quantum level means basically weak two-body interactions in a quantum many-body system, which you maybe want to start with. The short-range network comes when you put all these systems on a lattice, for instance, so on a lattice, and you have lattice points, some kind of discrete nonlinear Schrödinger equation, or you name it, some kind of cells which we have seen before and so on. So you have some discrete system, and then what you do is it's nonlinear, and then you basically just reduce the strength of the coupling between the sides. And in that limit, you will enter this other class of thermalization slowing down, which comes under the nickname of short-range network. There's another way you can reach or come into this short-range network by staying actually with the upper picture, but simply adding disorder, breaking translation invariance. If that will induce something called Anderson localization in your linear wave equations, then you suddenly switch from long-range network behavior to short-range network behavior. And that might be interesting, and that was our original maybe also motivation, that bringing together disorder and nonlinearities on a quantum level, disorder and interactions in a many-body system can somehow bring us close to the famous many-body localization studies, which have been around for more than a decade. Right, so very quickly on what I will not focus in detail on, this first approach, which we took for a couple of years, where we tried to extract timescales from finite time averages of observables. What we did there is we said, hand-wavingly, since we want to approach an integrable limit, and at that integrable limit there are well-defined sets of actions and angles, we'll take those actions, J, as the relevant observables, and then we will go off the limit, and we will look how they fluctuate and measure their time averages and try to extract all these time scales of thermalization. And that worked to some extent. And there is a number of papers which I just briefly flash in here, which were devoted to that. But there was an issue. There were several issues. And the main issue, these issues are written here, but the main issue is this one here. There's still this ambiguity of choosing the observable. If you want to show that the system thermalizes by studying its ergodic properties, you technically have to look at all possible observables. And if you choose the wrong ones, you can be fooled. You might think that you see thermalization, but actually the system is very far from being thermalized. So you can be fooled by the law of large numbers. This is what it is essentially. And even if I choose my observables, you may tell me, why do you choose these, choose others? So there's an infinite set of them. We'll never finish this job. So essentially there's a lack of aesthetic satisfaction, but also there's therefore a lack of precision of extracting clear timescales. And this is why we, 2 years ago, decided to compute the Lyapunov spectrum of such systems. Now, remind you, if you have a large system with, let's say, n degrees of freedom, then you will have 2 times n Lyapunov exponents. The number is simply equal to the phase space dimension. They come in plus minus pairs. And per each integral of motion, you will have exactly 2 zero Lyapunov exponents. And if you maybe have computed already at some point the largest Lyapunov exponent in the dynamical system and wonder how do you compute all of them, it's not that hard. It's not that terrible. Go to this paper by Benetin, Galgani, Giorgilli, and Streltsyn from 1980, or you can also find more fresh papers, and they will tell you precisely the way you have to program your system in order to compute them all. Let me start with results which were obtained by Mirab Maleshava, who was a PhD student with us a couple of years ago. We decided here not to first study a Hamiltonian system with a continuous time flow, but we decided to go for a system of unitary maps, nonlinear, but still unitary maps, because things go much faster when you process time in discrete units and you don't have to worry about discretizing continuous time, making tiny errors which maybe become big if you wait long enough, and so on. So, but essentially it's not much different from a normal Hamiltonian system. You see a one-dimensional chain. You see here these are the sides of your chain, and on each side basically you have one complex wave function number, call it psi n. And then what you do is you process this system in time by applying many times some unitary operation which I call here u. And u is basically processed in the following way. You first take nearest neighbor pairs of these sides, and you perform a linear unitary operation which is given by this 2 by 2 matrix, which is then again parameterized by this angle theta. So it's basically just a rotation on each pair of these sides. And then you repeat the same thing, but as you see, you shift the pairs by 1. So if you do that and nothing else, and repeat this endlessly, you will find nice linear propagation of linear waves in a one-dimensional system, just like in a Hamiltonian system. But it goes much faster because you go stepwise. The nonlinearity is added by these little green boxes here, which act on each of the sides individually and do actually nothing but change the phase of your wave function, but by a value which depends on the amplitude of that same wave function. And that is nothing but the usual nonlinearity in a nonlinear Schrödinger equation as you know it, if you integrate it over finite time to obtain the unitary operator which does the job. And that's it. So all these 3 steps together form this u, and then you repeat these unitary operations endlessly, and by that you will run a nonlinear, non-integrable system. Now, to remind you, this nonlinear term here, this nonlinear operation here has a little parameter g, little g. That's your nonlinearity. If g is 0, the system is linear. If g is non-zero, it's nonlinear. The linear operator C here, this 2 by 2 matrix, has this angle theta. If theta equals 0, it becomes a unity matrix, and therefore you completely decouple all the sides. So theta tending to 0 means very weak coupling, which makes your system obviously integrable because the sides don't talk anymore to each other, while on the other side, sending g to 0 at a finite value of theta will give you a linear evolution of a linear chain, which again is an integrable system. Also, what is important to mention is that the total norm of that system is preserved. It's because we have unitary maps. So if you sum over the absolute squares of all the psi's over all the sides, you'll get a total norm which is exactly conserved, and that takes the analog of the energy of a Hamiltonian system. Right. And now what we do is we will first look at the properties of the equations, and I will show you now where these two networks, short and long-range networks, come from. First, you just write down the map equations. It looks horrible, so let's not go into the details. But now let's assume first that we go to the regime of small nonlinearities G, and then we do an expansion. Then we do two things. First thing is we transform the system into normal mode space because we have translational invariance in real space. So from real space, we go to Bloch representation. And then we expand the rest of the map to lowest order in this nonlinear term G. And this is what you get. You get still a crocodile-ish equation here. But you see the C's are the amplitudes of the normal modes. These are the, so to say, the wave functions, the size of the normal modes. And if I put G to 0, then these things are conserved. You see, because you decouple them, you have linear normal modes. Each normal mode doesn't talk anymore to any other normal mode. And therefore, its amplitude is preserved. These are the integrals of motion or the actions at this integrable limit. And for small g, you get this right-hand side crocodile here, which is a multiple sum, actually a double sum if you take care of all the Kronecker symbols which happen to be in these overlap integrals I here. You still are left with a double sum over all the modes, which means each normal mode is coupled to triplets of many, many other modes. And that's what we call loosely a long-range network. So all the actions at your integrable limit become long-rangedly connected to each other in the presence of that type of non-integrable perturbation. Right. On the other side, if you go to the short-range network regime, that is, I remind you, small theta. And small theta means that this matrix here becomes more and more closer and closer to a unity matrix, which completely then decouples all the sides. In this case, you simply expand in theta. And if you do that, you get these simple-looking equations where each, in real space now, each complex wave function on each side is coupled weakly to its left and right neighbor. So that's a short-range network. If theta is equal to 0, you completely decouple, and now you preserve the norm or the absolute square of each wave function on each side in real space. So these are the two different networks. You see, you have one and the same system, but there are two ways you can go by changing the parameters of the system and reach two different types of integrable limits. And when you are slightly off these limits, you have two different classes of non-integral perturbations which will govern the thermalization dynamics.
What is superscripts A and B?
Say it again, please.
Superscript A and B?
That's just another way of labeling the system sides. Don't pay attention to that. It's just even and odd sides. Just makes it easier to write equations down. Right, so now what we do is now comes the hard part. So you take an initial state, which means you randomly excite your entire system. You distribute the norm on each side by a Gibbs distribution, and you choose randomly all the phases of the wave functions, and then you run the system, as long as you can. Now, to compute the Lyapunov exponents, we have to do more. We have to add a small perturbation, linearize the equations on paper, obtain a tangent map, a linear map, which has on input the data coming from the original nonlinear evolution. And we run these tangent maps. And actually, if you just run one, you will measure the largest Lyapunov exponent by looking how this perturbation grows exponentially fast in time. If you, however, want to compute all of them, you have to compute more of these tangent maps and do some tricky orthogonalizations in the map number 2 respective to map number 1, which will give you the second largest Lyapunov exponent, and then you go to the third map and you again do an orthogonalization, you get the third Lyapunov exponent and so on. You get all of them. It's fantastic. Even the negative ones, the entire zoo of them can be computed very nicely. It takes some time, of course. Right, then once we are done, we compute all these Lyapunov exponents and we sort them with their value, according to their value. The largest one is called lambda 1, and then comes lambda 2, smaller, 3, 4, 5, and so on, down to the first 0 Lyapunov exponent, and then I will not show you the negative ones, which of course still exist also if you continue this game. So, but then this entire spectrum, lambda, which now I have a spectrum lambda with a sub-index, this sorting index I, we rescale it by dividing all the other Lyapunov exponents by the largest one. So lambda I divided by lambda 1. And also the sorting index is made intensive by dividing the index I by the number of degrees of freedom. So that now this rescaled Lyapunov spectrum at rho equals 0 always starts at 1, and then becomes smaller and smaller, and at rho equal 1, it must come down to 0. That's it. And now we will look how this thing behaves in these different regimes. Before we do that, we also digged in the literature and found a paper by Ubini and Antonio Politi, who were off some integrable limits, but wanted to use some fitting function for these Lyapunov spectra, and came up with this 1 minus rho to the alpha function, which did a pretty good job. But for reasons to come, we had to dress it with another exponential, which then allows to measure the slowing down close to an integrable limit. So this is our fitting function. It has so far no microscopical reasoning. It just works fantastically well, which we will use. And here you see, here's a parameter beta, and here's a parameter alpha. And beta is the important one. And also, you can take the integral over this rescaled Lyapunov spectrum and come up with some kind of rescaled Kolmogorov-Sinai entropy kappa, which then, of course, is also a function of alpha and beta, and is a very good quantifier which will tell you in which of the two regimes you probably are, in a short-range network or in a long-range network. So this is how the raw data look like. You see these lines here, these are all the lines coming from these different tangent maps for the first, the second, the third, the fourth, and so on Lyapunov exponents. You do some averaging over time of this exponential growth, and when these lines here more or less saturate, then you maybe are happy and you read the first, the second, and so on Lyapunov exponents off. At some time here, like 10 to the 7. And you see one of these Lyapunov exponents still seems to go straight down to 0 as 1 over t. That's the one which has to be actually strictly 0 at infinite times, because we have one conserved quantity here. Okay, so we read this data off, and then we process them. Well, the first thing is maybe a bit more the boring. You look at the largest Lyapunov exponent, and you check that indeed the largest Lyapunov exponent becomes smaller and smaller as you approach an integrable limit, either by reducing g, the nonlinearity, or reducing this angle theta that is decoupling the sides. They do this in a different way, in some power law way, but we were not very much excited about that. That's not so interesting, so far maybe at least, but this is the interesting part. So now let's see what happens in this long-range network regime, which we achieve here by reducing the strength of nonlinearity. In this case, here is the rescaled spectrum lambda as a bar as a function of rho. Starts at 1, falls down to 0. At some distance from the integrable limit, you'll see some curve, something. Meaningless, some nice curve. Now, as you come closer and closer to the integrable limit, this curve somehow changes, bends a bit this or that way, but finally, surprisingly, it stays unchanged. It approaches asymptotically this dashed line and doesn't change anymore, which means that your entire Lyapunov spectrum, rescaled Lyapunov spectrum, very close to the integrable limit, will be some analytic function. And if you know the largest Lyapunov exponent, remind you this is lambda bar, which was all the lambdas divided by the largest one. If I know the largest one, I know all the other ones, and when I'm very close to the integrable limit. One time scale controls all the other time scales. Okay, but now let's see what happens when we go to the short-range network. That was when we make the coupling between the sites weaker and weaker. And there, again, at some distance from the integrable limit, the rescaled Lyapunov spectrum is some nice line. And as we approach now the integrable limit of weaker and weaker coupling, it again bends, but it bends further, and never saturates on some dashed line. So in a sense, the rescaled Lyapunov spectrum becomes non-analytic in this limit, 1 at 0 and 0 everywhere else. But that's maybe not the most important thing. The most important thing is if you now plot the same figure here on a log scale, log normal, you find that this decay, which becomes sharper and sharper here at small values of rho, is actually exponential. And the exponent of this exponential decay is the thing which diverges as you come closer to the integrable limit. So now we have, in addition to one diverging quantity, which is 1 over the largest Lyapunov exponent, which is already diverging, we have a second diverging quantity, which is this exponent. This exponent describes us how the other Lyapunov exponents, or the other time scales, if you wish, how they become smaller or larger, exponentially smaller or exponentially larger, as compared to the one which is related to the largest Lyapunov exponent. Right. Then you can add disorder, and this is a work in progress and will hopefully soon be put on the archive, where you can see that you can actually now cross over from long-range to short-range network classes by adding disorder, but I will not focus on that. Instead, how much time do I have? Let me first ask. 5 minutes? Okay. So very, very briefly, then there is a new paper which we put on the archive together with Gabriel Lando. And this one now is studying a truly Hamiltonian system, a system of coupled rotors in 1, 2, and 3 dimensions. For simplicity, I only show you the one-dimensional Hamiltonian. You can also say this is a model of a classical model of superconducting grains, which are weakly coupled to each other by Josephson junctions. And you see the energy is conserved. This is the kinetic energy, if you wish, of each rotor. Or it's the charging energy of a superconducting island. And this is the Josephson energy of the coupling, or if you wish, it's the coupling between the rotors. The Q's are the angles of the rotors, and so you have a cosine coupling between them. The total number of sites, again, is n, let's say, and the energy density then is capital H divided by capital N, called small n. Okay, and then again, you can find the same two regimes of short-range and long-range networks in the system. If you take that system, and now you only have to change the ratio of the energy density to the coupling, Josephson coupling energy Ej. If you go here into the limit of very small values of this ratio, then basically you come to a harmonic chain which is integrable, as we already discussed before. And then when you add the first non-integral perturbation, it will be simply coming from the quartic term of the expansion of the Taylor expansion of the cosine, and then you get some kind of FPU-like chain with very weak nonlinearities, and that will give you a long-range network. And you can even here write down the equations in action angle representation, and again see how these actions at the integrable limit become coupled in a long-range network-like way with all the other actions in that network in a more or less without having any distance anymore in this network. The same can also then be done for the short-range network limit. There you simply crank this ratio H to Ej to very large values, which essentially means that you decouple the rotors, and in the very limit, you end up with a system of free rotors, which is again an integrable system, and the Josephson coupling is then the weak non-integrable perturbation. And again, you can write down the equations now in action angular representations and see that it's a short-range network. And then this is my last slide with the results. And then what Gabriel did is he ran these systems in these upper two plots here, 2 and 3 dimensions. And he found, again, that for long-range networks, that's the green results here, the green lines, the rescaled spectrum always saturates on some dashed line as before of the rescaled Lyapunov spectrum. And so only one quantity diverges, which is the inverse of the largest Lyapunov exponent, and then all the other Lyapunov exponents can be measured off from these dashed lines. While if you go now again to the regime of weakly coupled the superconducting grains in 1, 2, and 3 dimensions, you find again that there is exponential decay of this rescale spectrum, and you can now very cleanly measure also how this exponent, beta, if you remember that quantity, depends on the distance from the integrable limit and how it diverges. And that's actually one of the maybe current holy grails here in the problem, which is come up with a theory which tells you how to compute this exponent beta as a function of the parameters of the system. I have no idea how to do that. Right, with that, maybe I should come to my end. So some take-home messages. We observed 2 distinct universality classes of thermalization slowing down upon reaching an integrable limit. The classifier is the network type which is imposed by the non-integrable perturbation upon the actions of the integrable system. We find long and short range behavior with very different outcomes as it comes when we look at the thermalization timescales. You can also add disorder and play with Anderson localization to induce transitions from one to the other. And this works more or less in any lattice dimension. Finally, just some open issues. Are there more classes? We need quantitative theories, explanations, predictions. There are other interesting integrable limits we know, like Toda, Ablowitz-Ladek, simply the ideal gas. And also actually simply continuous time. So maybe I just used my last half of a minute for that. So say you take a Toda system, a Toda chain, which we know is integrable. It's integrable when you define it using continuous time. But if you now integrate it on your computer, you will always, or usually at least, discretize time. And even if you do the best thing and use the top-notch integrators, symplectic integrators, you'll still have to discretize time. And if you do that, you will break integrability. So that's another way of going off from an integrable limit and studying what happens. And there's a recent, you don't see it here, a recent paper which we just put on the archive. With that, I thank you very much for your attention.
Thank you. Thank you, Sergej. Questions? Prashant?
Can you simply go from short range to long range by choosing connections like 1 over x raised to alpha, and maybe at the limit alpha becoming 1, you will get
what is alpha?
Some power. You choose, you couple.
Okay. I guess I understand your question. So yes, we could of course do this very abstract approach and say, here is my integrable system written down in action angular representation, which means I have a Hamiltonian which simply depends only on a set of actions. That's integrable. Now I add some non-integrable perturbation by hand, which will impose a network of couplings between these actions. And if I now choose different types of networks, and we know there's a whole network science on different types of networks, then we could expect maybe to see different, more additional classes of thermalization slowing down. True. We didn't do that. That's one possible way to find more universality classes. Thank you.
Hilda? Yeah.
Oh, thanks. Thank you. Very interesting talk, really. And I mean, have you thought of taking, for instance, the case of the Josephson junctions and do some experiments? Because if for instance, if you take your system of Josephson junctions and you take Josephson junctions in series and then you shunt them, the system becomes globally coupled. Okay, so you could by increasing, going as near as you can, as you say, to the infinite limit by increasing the number of junctions and just shunting them on that. Of course, you don't go to all kinds of topologies of your network, but you can do the global coupling in that case, and the experiment shouldn't be that complicated, I think. from a theoretical
No,
point
yeah,
of view.
I fully agree with you. Right.
Sorry?
Yeah. I fully agree with you. For us, it was, so to say, the most surprising thing was actually that there is life in chaos, that there is structure in chaos, so to say. But now that you understand that, you can maybe search for even more, for many more the classes. The minimum number of classes is 2, otherwise you cannot claim that. So, but probably, yes, there are more, and there are different ways to find them, and you just mentioned maybe one possibility to follow.